Welcome everyone. In this video we are going to derive the function for simple harmonic motion. So what is simple harmonic motion? I will abbreviate it as SHM. I use the initials of the three letters. This is simple harmonic motion. There are two characteristics that you really should know. One is that the magnitude of the force is proportional with the displacement, the magnitude of the displacement from the equilibrium position. And the equilibrium position is the point where the net force is zero. So we have that force is proportional with displacement. And the second one is about the direction. It says that force, so F with the arrow this time, it is vector, F is opposite the direction of displacement from the equilibrium. Now, since it is opposite, this property is represented by an adjective, and that adjective is restoring. We often call these types of forces restoring forces because they are pulling you or pushing you back to an equilibrium position. Alright, so we have this. Now, with this said, we can combine these two statements into a powerful equation. And that equation is, so we have F, it is proportional with x. So if we put a kx, we will have an equality. However, this isn't enough because we need to bring vectors into play as well. That's why we put a negative here to emphasize the direction. Alright? Now we have this. And on the left, we notice an important thing. We have F here. Whenever you see F, three letters should come to your mind. I mean, most of the time, not always. Those two letters, did I say three? Those two letters are M and A. Because force is equal to mass times acceleration. At least the net force. And this is Newton's second law, which I proved in a previous video. You can find it from the cards right now, also from the descriptions part. Now, with that being said, I want to now focus on A. What is A? What is acceleration? It is going to be the second order time derivative of position, which is basically dx by dt. Let's see, where do I put the squares? Like this. All right? So this is acceleration. And you can put the arrow even. Now, and this is completely okay to show acceleration like that, but there is another way of showing, which was first introduced by Isaac Newton. And he is a physicist, he is an important physicist, that's why we still sometimes use his notation. And it is also a very short way of writing it. He called this x double dot. And this dot means the derivative, but not just any derivative, the time derivative. So you might guess what is x dot then. It is going to be velocity, because this one dot means the first time derivative of position, which is velocity. So we will substitute this, which is, as I said, just another way of representing acceleration. So when we do that, it becomes mx double dot. Alright, so far so good, I hope. So we have this, and now I am going to add kx to both sides. So I'm now focusing on this and this. Let's add kx to both sides, and when we do that, what happens? We have mx double dot plus kx, it is going to be equal to 0. Now, this is okay, you could leave it like this, but there is a more convenient, more conventional way of writing the simple harmonic motion function. And that form is achieved when we divide both sides by mass, by m. So when we do that, we have x double dot plus k over m, the displacement equals 0 divided by m, that's just 0. Here you could again stop, but no, they didn't stop. At least scientists chose to give k over m, this factor, a name. It is defined to be omega squared. And this omega is called the angular frequency of the simple harmonic oscillation. Alright, so when we plug this in, we then get the final equation. It is x double dot plus omega squared x is equal to 0. And this, my friends, is what describes a simple harmonic motion. Whenever you encounter this formula while analyzing a situation, then you know that you're dealing with a simple harmonic motion. I hope this video was helpful. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.